morning everyone. So my name is Kun Jin Jun.
My name is Daniel Kong.
My name is Anna Sophia Fikari.
And I'm Wen Tao.
And we are from Group 14 from Wednesday class, and today we're going to be presenting about our Nozzle project.
As a team, we are required to design a nozzle that would entrain as much water as possible into the measuring cylinder by utilizing Bernoulli's principle. Air is pumped through one side of the nozzle to create a low pressure region for the water to be sucked into the nozzle, which will eventually be pushed into the measuring cylinder. We are required to improve the design of our nozzle by changing certain features such as diameter of the nozzle, placement of the holes in the nozzle, and the angle of the diverging part of the nozzle. Our score is taken based on the mass difference of the measuring cylinder before and after 5 pumps. Initially, we chose nozzle C as our basis for our first attempt, as we thought longer and thicker nozzle would prevent the air escape from holes in the nozzle. Basically, we started off with nozzle lengths close to the maximum 115 millimeters to maximize pressure difference. Our first 4 nozzles have a short converging section followed by a long diverging section. We wanted to test the idea that more gradual converging and diverging sections will reduce the energy losses, increasing the amount of water collected. During initial testing, this design obtained 20 grams of water. We also observed air leaking out of the inlet pipe, therefore Teflon tape is used to reduce leakage for future tests.
After the first 2 nozzle attempts, we figured that the straight narrow section in the middle would be too small to hold much water. So we placed the holes further down the diverging section, where the cross-sectional diameter is bigger, in the hopes that more water can enter the nozzle. Other than that, we also increased the total number of holes from 4 initially to 8 by the 4th nozzle in a circular pattern to maximize the flow of water into the nozzle. The diameter of the holes also increased slightly from 1 mm to 1.75 mm to allow the smooth inflow of water. We also made slight changes by moving some of the holes slightly higher to prevent the nozzles from breaking. The testing showed some improvement, where the water collected increased to 26 grams. We also started using hot glue to seal the inlet pipe to ensure the air is fully pumped into the nozzle.
However, we wanted to test the extent of how much water a nozzle can actually carry into the measuring cylinder. For our next design, we made a much bigger cylindrical chamber with a diameter of 36 mm that has 7 mm holes between the inlet and outlet to contain as much water as possible. Within the chamber, the narrow middle section is removed to allow the accelerated air column to freely push the water to the outlet. However, during testing, the nozzle failed to gather any water at all. We observed that the air column lost energy and escaped through the holes on top. Hence, we conclude that the middle gap is too huge for the air column to travel the distance.
For our next and final design, we incorporated findings from our previous test and shortened the chamber and the middle gap of our nozzle considerably to a total length of 9 cm. This allows the inlet air column to travel a shorter distance to the outlet to minimize losses. The chamber has 4 holes with diameters of 4 mm for water to flow in. The air is expected to push the water and leave behind a region of lower pressure in this area, which will be able to draw in more water towards the outlet. This design worked really well and achieved a much higher result during demonstration at 49 grams. In conclusion, by utilizing findings from previous designs, the final design performed much better and achieved a good result.